Check it out now, y'all.
NanoHub U, online instruction.
Hi, welcome back. We're moving through a discussion of wave functions this week, and I guess to start this lecture, I'd like to just briefly review what we covered in the previous two lectures. We discussed free particle wave functions. These are wave functions that are completely delocalized in space, and we were able to calculate how these wave functions interact with potentials that have abrupt discontinuities at a certain region in space. And we were then able to calculate the probability that these particles, which are represented by these free particle wave functions, we were then able to calculate the probability that these particles, let's say, transmit over a square step barrier. Now, the way that problem was solved was it relied solely on representing the particle by a wave function of the form a e to the I k times x. This is again a one-dimensional wave function that describes a particle moving from left to right along the x direction. And what we've already shown is that if you take this free particle wave function, put it back into Schrodinger's equation. Now, Schrodinger's equation is modified here because the potential energy term U is set equal to 0, right? That defines a free particle. When you put this solution, or this proposed solution, back into Schrodinger's equation, you get a simple formula for the total energy of the particle. And we find that that energy is proportional to this wave vector k sub x in the x direction quantity squared. And we also have shown that this particular free particle wave function is an eigenfunction of the momentum operator. So if you just put that wave function in, you operate it by the momentum operator, which is minus I h bar partial with respect to x, right? What you get back again is h bar k sub x. This is just the momentum of the particle in the x direction. So the problem with this wave function is when you try to determine this coefficient a, right? The normal way that you determine that coefficient a is you insist that the wave function times its complex conjugate integrated over all space that's equal to unity. So this is the normalization condition. And for this particularly simple wave function, when you take e to the I kx and multiply it by its complex conjugate, the exponentials disappear. You're then left with the product of a complex conjugate of a times a, and you're left with this integral from minus infinity to infinity over dx, and you want that equal to 1, right? That implies that particle is localized or is found with unit probability over the range of this normalization integral. And of course, you can immediately see the problem, right? The integral of dx from minus infinity to infinity is not a finite value. So this normalization doesn't work very well. And very often what we end up doing is we end up setting this coefficient a equal to unity and performing calculations with that assumption. But this lecture and the next 2 or 3 lectures is really a discussion. It's an extended discussion on how to better write down a free particle wave function, something that's a bit more realistic than this delocalized wave. And it requires a discussion of a few topics, some of which are mathematical. And then the final topic is Heisenberg's uncertainty principle, which we'll discuss, and it follows directly from the first 3 topics here in this slide. So the first topic is a Fourier series. It's just a review of something that most of you have already learned. The second discussion is going to be about Fourier transforms and Fourier transform integrals. I suspect maybe 50% of you have heard that story. It just depends on what courses you've already had mathematically. Once we understand the Fourier transform integral, then we'll be able to form wave packets, and we'll be able to show how those wave packets actually provide an improved wave function for free particles. So to begin this, let's review some of the mathematics behind the Fourier series and try to emphasize some important points that are going to be relevant to this entire discussion. So to begin, right, in many endeavors of science and engineering, we encounter signals that are periodic. And this periodicity either can occur in position, so for instance along the x direction, or the periodicity can occur in time, along the time axis. And irrespective of whether we're dealing with position or time, there's always some repeat distance. In the case of position, that repeat distance is a distance capital L. In the case of a time signal, right, that repeat distance is this period capital T. So in this discussion, we're going to focus more on the signal that repeats with position, right? So we'll be referring to L as the repeat distance of a signal that's periodic in X. The interesting thing to realize is that these repeating signals are well understood using trigonometric functions. And so, for instance, if we have periodic functions like sine x, cosine x, sine 2x, cosine 2x, all the way out to some integer n, sine nx, cosine nx, these functions can be combined in a very clever way, and they allow you to represent the periodic function of interest as an infinite series of periodic sines and cosines. The advantage of sines and cosines are that the properties of these functions are really well understood. They're so simple, they're taught in high school. So for instance, there's pages and pages of trigonometric identities that you've probably had to prove. The calculus of the sine and cosine functions are well understood, so you can easily take derivatives. And one of the important features of these sines and cosine functions is the orthogonality, which is expressed by these two integrals down here. By orthogonality, we just mean that if the period of one cosine and the period of another cosine are different from one another, the integral over, let's say, one period of the cosine functions, that integral is always equal to 0 if m is not equal to n. But if m happens to equal n, then this integral is non-zero, and we get this constant pi out. There's a similar result for the sine functions, right? So this is referred to as orthogonality, and it plays a critical role in deriving the expressions for Fourier series. So the Fourier's theorem goes back to 1822. It's almost 200 years old by now. So it's very well understood. And what it basically says is that any periodic function of position or time that has a well-defined periodicity, either capital L or capital T, that periodic function can be written as a sum of sines and cosines. And the Fourier series of some arbitrary function f of x that repeats itself can always be represented by this equation that's written down here as equation 1. So to be useful, we have to be able to determine these unknown coefficients. There's an unknown coefficient, it's constant, it's an A0, it's just an offset independent of x. And then there are coefficients a sub n and b sub n that depend on the cosine and the sine functions. And the trick is to figure out what A0, A sub n, and B sub n are based on the known function f of x that's usually given to you. And the answer to that question is there are well-defined integrals that define A0, A sub n, and B sub n. All these integrals involve integration of the function f of x over one period, over one repeat distance. So these integrals always go from 0 to L, from minus L by 2 to plus L by 2. It just depends on how the function is specified. If you can perform these integrals, then you can uniquely determine the values of these coefficients A0, A sub n, and B sub n. So you give me the value of n in this sum, I can then, in principle, calculate the various coefficients that are appropriate for that term in the sum. So the next few slides, I actually just go through and I derive the result for I picked the B sub n equation on the previous slide, right? So I show you that this coefficient B sub n can be determined in terms of an integral of f of x over one period of a sine wave. The arithmetic is pretty straightforward. You can work through it if you'd like. It's a little bit involved, but at the end of the day, what you can show is that this coefficient B sub n is given by this equation here, which is the same equation that I wrote down a few slides prior. So you can do the same analysis for the coefficients A0 and A sub n. I'm not going to work through that. The arithmetic is very similar to what's shown on these previous 2 or 3 slides. And hopefully you've all worked through that at least once in your career here at Purdue. The bottom line, okay, is that these coefficients A0, A sub n, and B sub n can be determined. If you give me a periodic function f of x, I can write that periodic function in terms of these infinite series that involves both cosines and sines. So there's a couple of comments that I can make at this point, hopefully to clarify various issues, because depending on which textbook you look at or which math book you read, this Fourier series is written in a number of different ways, and what I hope I can convince you of is that these different ways of writing it are just cosmetic, and they just reflect the emphasis on what the argument in the sine and the cosine are going to be. So if you want to explicitly emphasize the repeat distance, capital L, then what you tend to do is you tend to write the cosine and sine arguments in terms of capital L, right? If you're more of a wave vector person, right, if you want to emphasize the wave vector k of these contributions to the function f of x, then you can rewrite the Fourier series in terms of a parameter k sub L, where k sub L is defined as 2 pi over L, where L is the repeat distance. So this emphasizes integer multiples of k in the Fourier series. And then lastly, if you're interested in wave phenomenon, very often it's useful to specify the wavelength of the various contributions to this Fourier series. And to do that, you then tend to write the argument of the cosine in terms of the ratio of x to the wavelength of the nth contribution in this infinite series. And this wavelength L sub n is then defined as the repeat distance, capital L, divided by the integer n in the summation. So all three of these things basically do the same, accomplish the same function. It's just a question of preference which one you choose for a given application. So you shouldn't be confused about the notation. Rather, you should be able to focus on what the Fourier sum is trying to accomplish. The other thing I like to mention is that this is an extremely important result for any sort of math or physics, any sort of physics or engineering applications, because what it does is it implies that if you really understand the properties of a sine wave or a cosine wave, then you can understand the properties of a wave, a repeating wave of any shape given by f of x, simply by realizing that this function f of x is just a sum of sines and cosines. So this should be of comfort to anybody, because no matter how complicated f of x is, it's nothing. It can always be represented as a infinite sum of sines and cosines. And if you understand how sines and cosines work, then you understand each term in the series. And so therefore you, in principle, can understand how any complicated function of x behaves. So that's one of the great benefits of Fourier's theorem, and it's why Fourier series are used everywhere in science and engineering. So to try and nail down these ideas in a bit more concrete fashion, let's consider a very simple example, and let's just work through it. Just make sure that we all understand how the arithmetic works in this case. I'm going to take a periodic function which is comprised of a sequence of pulses, right? These pulses are periodic in this distance capital L, so every distance L along the x-axis, this periodic square wave repeats itself, and we're going to say that the width of this pulse is designated by a parameter capital L sub p, right? So we've got a repeat distance, we've got the width of the pulse, and we've also got a coefficient a that emphasizes the amplitude of the pulse, okay? So that's going to be our periodic function f of x. And the question is, we want to know what the coefficients a0, a sub n, and b sub n are that represent that periodic function. And the answer to that question is straightforward. You simply have to take the definitions for a0, a sub n, and b sub n, and you have to apply it to this particular function f of x. So all these coefficients are determined by integrating over the repeat distance from 0 to L. And in this case, this integral can be simplified further because there's a large region of this function where it has the value equal to 0. So in fact, over this entire range of the integral from 0 to L, there's only a small region, L sub p, where the function is non-zero. So that immediately allows you to rewrite the integral and express the limits from 0 to L sub p. Over that range of x, the function has the constant value a, and that's what you then put into this integral. So all these problems are the same. You have to take the function that's given to you, and you have to then analyze it, and on the basis of that analysis, you then have to tailor these generic expressions for the various coefficients to the particular problem that you're working on. So that's where you have to do something, right? You just can't sit passively by. You've got to interpret f of x and modify the equations for a0, a sub n, and b sub n accordingly. So this is the expression I get for a0. It's a trivial result. It just says that a0 is basically this constant a weighted by the ratio of L sub p over L. I work out the expression for a sub n in terms of the sine functions, and on the next slide, I work out the expression for b sub n using the same type of arithmetic. To make the discussion that follows a little bit simpler, let's pretend that L sub p is equal to 1/2 L. So we're going to intentionally pick L sub p equal to L by 2, and what we then find is we find this expression for b sub n simplifies right? And it gives us a value gives us an expression that I evaluate here. Turns out all the coefficients a sub n are now equal to 0, right? So with this assumption, there's no coefficients a sub n. The b sub n coefficients only exist for odd values of n, and our constant a0 is now equal to 1/2 a. So this simplification is strictly a result of the symmetry of f of x about 0, and it often occurs in these simple expressions for Fourier series. What does it all mean? Well, it basically means that we can now represent this function f of x, which is this sequence of pulses. Each pulse now is going to have a width that's equal to half the repeat distance, right? We can represent that function f of x by this Fourier series, which I write down here. There's no contribution from the cosines. Those all drop out. We've got 1/2 a plus, that's a constant offset, plus this term that involves a sum over just odd integers n. We can evaluate those various coefficients, right? And I do that here. So I plot, first I plot the value of a0. It's just equal to 1/2 if I pick the coefficient a equal to 1. And then the various coefficients b sub n are plotted here. The size of those contributions, the first one is 2 over pi. The next one is 2 over 3 pi. 2 over 5 pi, 2 over 7 pi, 2 over 9 pi, and so on and so forth. So you can see the contributions to that square pulse drop off with higher index value n is 1 over n. And of course, what you can then do is you can take these coefficients, you can put them back into this Fourier series, and you can then reconstruct the function just by evaluating each term in the Fourier series and adding them up. So I do that here. I plot the original function in red. The original function in red goes from 0 to positive 1, right? The coefficient L sub p is now equal to half of L, so L is given by this distance here. L sub p is just half that value. Right, and I just keep the first 9 coefficients. I'm sorry, I just keep the first 5 coefficients, 1, 3, 5, 7, and 9, right? And that's represented by the blue curve here. And what you can see is that just keeping 5 of these coefficients, you start to get a function that roughly approximates the square wave function that we use for f of x. If you want to do a better job, if you want to make a more accurate calculation of f of x, you clearly have to keep more and more of these harmonic terms. And in the limit, when you keep them all, according to Fourier, the blue curve will precisely match the red curve. So this is a brief summation of Fourier series. I think everyone's probably seen this discussion at some point in their academic career, and I just use it to introduce the basic concepts. The next discussion is going to be about Fourier integrals, and we're going to motivate that in terms of these pulse-like functions, and we'll discuss that in the next lecture. So we'll see you in a few minutes for that one.